Message was impossible.
Hello, hello. Hello. Okay, hi. Okay. You guys can hear me or no? Can you hear me? Can someone acknowledge if they can hear?
I can hear you.
Great, thank you. Okay, and you can see why you can. Okay, I'm running a couple minutes late. I apologize for keeping you waiting. Wait, you can see me too, right? Or it's a little dark or something. But,
Yeah.
Yes. Okay. So you got I predicted things might be late, and they were even later than I predicted. I hope it's clear that the thing that I was very late in sending you, you were not expected to do anything with. I mean, and I knew at a certain point that was, I hope, clear that you weren't going to be expected. But hopefully, as of about like a minute ago, and I need confirmation on this, hopefully you all got a document, what do you call it, a draft. I mean, there may be revisions and stuff to this document, but you got a document which is supposed to be the practice exam for the exam that you're supposed to have this Monday. This is, and we're going to spend a lot of time today talking about this, actually probably almost all the time dealing with this, to make it as less stressful, not more. But first, can we confirm, did you get a PDF through Google Classroom that you can open that's like 20 pages long, that is a practice exam? Can come and confirm if you like received that?
Yes.
Yes.
Is that the
Okay.
actual length of the exam?
Right. Very good question. Very good question. And the answer is no. The actual exam is shorter than that. But I'll get to all those kind of questions. I'm going to have to do this a little bit systematically because otherwise it does cause stress. So, all right. So you got a document that first of all came 2 seconds ago, so you couldn't have done anything with it. Second of all, if you even start opening it, it may look intimidating or crazy. We're going to deal with, and it is meant to be. The whole point is that the exam itself is never meant to be a surprise sneak attack. The practice exam should always, in some sense, be more scary than the actual exam. Like, that's the point of it. But anyway, hopefully everybody I'm going to go with the assumption now that everybody has the document and is going to like have it ready to go for this period. Like, we're going to work on it. So whatever is easiest for everybody, like whether you have a separate device or you print it out and you like have it in front of you, however you do things, like we're going to work on this document today in a big way. So I'm glad everybody, if they have it. The other thing is I just want to check, because this was an experiment. Also at the last minute, did people, like just a second ago, did anybody get any PDF in Google Classroom through the stream that was in some way, wait, what's happening? Oh, that was, excuse me for 1 second, excuse me. The two device thing is bad. Did people get the class notes from one session of class notes is what I said?
Yes.
Just as yes, great, all right. So they may be very weird, they're just raw, this is an unedited file, it's whatever it is. But if that worked and you got it, that means it wasn't that big of a deal to send. So I'll send the others in due time. I didn't even bother to file name that. But I think it was yesterday's, but it may have been the days before, but I'll get you yesterday's. Yeah, it says something like class notes. So it's meant to be on Classroom. Yeah, I sent it on Classroom. Yes. Yeah, anyway, and we're gonna get to the homework and everything. Like everything is, this is an accelerated course. The first couple, I try to break down as much as I can, but certainly the homework has ramped up, and all of a sudden we're talking about an exam. The material has all of a sudden exploded, and anybody who might be intimidated or nervous, that's fair, and we're gonna try to address that. But let's just all assume that that's the case. Can everybody mute, please? There's a problem that might be partly me and feedback, which I'm gonna fix right now. because I have to do it. But if you can mute yourself, great. Thank you. No, it's not me because I'm not even joined yet. Okay, thank you. That's helpful. All right. So if you got those class notes, again, I'm not making any. I don't know what's inside. It's oh no, I do. I mean, the point is that every one of these lectures is recorded, and you should have access to the recordings, which are 3 hours long. But then someone intelligently asked yesterday, can we just have like a PDF of just everything I wrote down? And I hadn't thought of that, but that's a great idea. So that's what that is supposed to be. That is just raw from my tablet. Again, if you got it at all and you can make any use of it, then I will send them all. I mean, I'll send, I think that was yesterday's, I'll send the day before. But that one I'm not going to organize for people or anything like that. It just, you know, it's great if you want to, but anyway, but they're just a PDF of the written notes and the recordings. I guess I want to confirm this too. Can anybody confirm that a recording of yesterday's class did become available at some point last night? Or am I behind the class? Can anybody confirm whether yesterday's, I think,
Yes, it did.
It did, great, thank you very much. All right, so these are all good things. I still know everybody, I now feel behind in the homework already. That is, most of you have handed in more than you've gotten back already. That's good for you, of course. You may feel like you're behind. Any one of you, if you have not finished, like technically by today, homework 4 was due, but if you have not finished that or even started it, that does not mean you're like dying in this class at all. You do, every one of those homeworks, the material will have been covered in this exam that we're going to spend today talking about and everything. Like, it is all related and the homework will help you. But I'll be quite frank, I mean, let's be real. Thankfully, the reason I do the practice exam is what we're going to do today is shift gears, hop directly to the practice exam and sort of talk about it, get a sense of what the exam is like. Of course, it means there's going to be work to fill in over the weekend, like you'll have to do it. And some of you may see retro doing homework while you're doing it may help, or if you think a homework assignment is irrelevant, then don't worry about it. Like, obviously we're all worried about the exam right now. Oh, let me make that clear. Will I accept any late homeworks even after the exam? Yes, I will. I mean, you know, maybe it would be dumb for you not to have done homework 1 by now, or without talking to me, but I'll leave the portals open for certainly anything we haven't talked about. So if you're worried about your grade, you want to shift your focus to do everything that will help for this exam. That means knowing this practice exam that we're about to start talking about today. The practice exam is meant to cover everything that could possibly be on the exam. The actual exam is always like a large portion of it, but not all of it. The actual exam is never longer than it, but this is to prepare you in every possible way. There may be errors or updates to this practice exam. If you get an update from me, like tonight, or that means either I found an error and I'm correcting it, sending it to you, whatever's the most updated, you know, that deal with that and throw away the old. But any change I make is always because I try to make your exam based as much on literally what you learned and what we emphasized as I can, like not some dream or theory of some other class. And I try to make the practice exam look as much like the real exam as I can. So as we're reviewing it and stuff, or as I'm seeing where the class is, I promise you, if I feel like, oh, you know, we didn't really cover this adequately or blah, 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 but this class really seems on top of blah, 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 that means I'm mentally changing the exam in my mind. And so any adjustment I make to the practice is to bring it closer to the actual exam and help you more and surprise you less, I promise. In other words, I'm going to apologize in advance that there may be updates to this, but that means it's trying to get more aligned with the actual exam. You are not going to hand this in, none of you. The practice exam is for you to know the ins and outs of the exam before it happens. And again, roughly speaking, the practice exam will be like identical in format and content, you know, with numbers changed, of course, but it would be like 85% identical, shrunk, but identical. Okay, there won't be a lot of surprise. The more you know this thing, the more you'll know the exam. Again, I'll be more, but you're not handing this in. This is for you guys to work through. You will, by the end of the weekend or whatever, you will throughout get more and more solutions to it, so you can more and more see what I did. In the copy I've just given you, there are already solutions to some. I just didn't even bother taking them out because whatever. There's already solutions to some, so you could see an example, but there aren't solutions to others. Those will come. Well, obviously on the real exam, you won't be given solutions. The equation sheet that's given here is like what it will look like on the real exam. The way questions are presented, blah, 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 same thing. Hold on, and we're gonna get to really, I even have very specific advice of exactly how to do a practice exam, and it does involve doing it multiple times, but you know, we're gonna start working on it today, so I'll give you more of those pointers as we go. Oh, okay. I think the one thing you'd want to know probably, oh, when you start looking at this, you'll see, if you flip around, you'll see some problems that are like, oh yeah, we were doing that in class. Oh wait, he started that in class, but he didn't finish yet. What the hell? We'll find out all that today. I mean, I think anything that's in there, I have finished in one way or another, or asked you to look at a video, but we'll find out what we need to find out today. And if it's there, and some things you'll be like, that doesn't look familiar. But if you think about it, you'll see how it's totally is an exam problem based on what we've done. And the point again is, if it doesn't look familiar and you have to think it through, that's what you're doing now. You won't be in that shock moment when the actual exam comes. Now, finally, I know I'm babbling way too much. As far as the actual exam is going to be take home anyway, okay, which means something very specific in physics to me. What's happening with this whole practice thing is you're going to have this all weekend to grind through and know inside and out and find out what you don't know and all that. Then we're going to have class Monday. Like technically the exam is Monday, right? But this is what's going to happen. We're going to have class Monday. There will still be an opportunity for me to feel out how people are doing. Like I won't change my mind and change the exam or something like that. But, there might be a question here or there that someone wants to ask me. And depending on how that question is phrased, I might be more and less generous with our class time Monday, but you'll come in Monday having done this practice exam and ready to go. And we'll have class moving to some extent to new material that you'll just have to write down for later, and to some extent addressing questions. Then when the class is over, maybe 15 minutes later, I will post what is the actual exam. Okay, I'll post it as though it were a Google assignment, except that it's worth more, but I will post it as the actual exam once class is over. And you'll have, almost definitely, but I'll confirm this by then, you'll have till the beginning of Wednesday's class probably to actually turn it in. Maybe I'm going to change my mind. I mean, don't swear. Maybe I'm going to change my mind and say you have till the next day if I get enough feelings from, but I don't think you have a lot of time at night to do a lot, especially with lab. So most probably it'll be posted at the end of class, and then you'll have between 20 something like 36 hours to do it any way you want, like non-test conditions. This is like a surprising to a lot of people, and you might even not, you think you're not hearing me correctly, but it's going to be a take-home exam, which means actual take-home, as though it were like a US history paper or something like that, or like a DBQ from high school. It's like a take-home project that you're doing. Only you will have, if you've studied, you'll already know what the project is mostly, and you'll already have all your notes and everything from your practice exam. When I say this thing is take-home, and I'll get more detailed about this at the end of this class, but I want it to be clear right now. I'm many things. I'm a pushover in many ways, but I'm not like dumb about this stuff. When I say take home, what I need is open universe, open everything, open the web, open your notes, open your friends. I don't care. We'll talk more about, you cannot cheat on this exam because everything that you think of as cheating is not cheating, and everybody can do it. Whatever you're thinking. Again, I'll explain, and this is not because I'm a pushover. I am a pushover in many ways, but this is more because I've been doing this long enough to know that this works. And this is what they did to me when I was in college and graduate school. It's a take-home exam where you still can help each other, and I hope you do. Maybe you've already helped each other enough by the weekend that you don't need to, but you still can talk. You can't talk to me, or I won't give you answers, but you can still talk, and you can call up Aunt Bertha, or you can wiki like Khan Academy, blah, 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 blah. And what all that doesn't mean is that it doesn't mean that I'm making the problems extra hard just to mess with you, not at all. But it means that after you've done all that and done whatever you want to really know this thing inside out and get every bit of help you want, then by the time the exam is due, you have to have filled out the whole exam in your handwriting with your name on it and give the most thorough explanation to all the answers and everything on the whole exam that you possibly can with your understanding that you are now reporting on having gotten it from the whole collective community, or what some people would call cheating and I would call research. You're going to turn in an exam that says everything that you understand about all the problems. It's clear when people understand what they're writing down, and it's clear when people don't. And you know that as well as I do. You're not going to have to give credit to anybody for helping you because I don't, every time I say F equals MA, I'm not claiming to make up the equation, neither are you. You're claiming to understand everything, and the way you're going to show that is by writing everything in the final document with your name on it and doing it your way. Just like all the homeworks, you can help each other, but some homeworks are just obviously more beautiful and on target than others. That's what the exam is. You have all weekend to practice it all together. And then when you have it, you got like 36 hours to just blast the crap out of these questions in your final way with your name. And the goal is for everybody to rock the crap out of it and show that everybody could get an A, which they could, because I don't have a requirement that people have to get Fs or anything like that. And because physics is hard enough that even saying all this, I'm telling you, even with all this, enough people will actually do badly, whether by cheating or not, that it makes for a very fair and perfectly challenging test to everybody, and also cuts out all the Zoom crap garbage. So that's a lot to say, but that's also the way your final exam is going to be, probably. All right, it'll be take home full universe, but then in the end you report what you've learned for that exam. You might be learning things along the way, and then great. So today what's going to happen in a minute, because I've talked too much already, I still owe you stuff. I'm going to try to catch up, but in a minute I'm going to put you in breakout rooms and you're just all going to start working on this exam. Like, flip to wherever you want, anything you think, like, act as though this is an actual exam. It is not. You're not. I'm not looking, blah blah, but act as a, holy crap, he just tossed this at us, like, what would you do? But assume you have full notes, full friends, full everything. One thing I do apologize, I forgot to put, or I didn't correctly put in point values and stuff in this document. Probably in an updated draft I will, but so you don't necessarily know how much points things are worth, but just assume that by the time you turn this thing, what you want to do is fill in everything. So in a minute, after I get some questions, I'm going to put you in breakout rooms. We're going to start working on this as though it were lab period or something. And I will come around, I will, but I won't, but at first it'll be, I want you to try. And then again, I will talk about it, we'll address it, blah, 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 blah. The first, one of the problems is overly written with a lot of weird writing that's too jokey and asks too many questions. It's like, it has a lot of graphs. You'll know when you see it. Don't take it. You don't have to make graphs, even if it sounds like it for a minute. It's talking about graphs, but you don't have to like create graphs from nothing, even if it sounds like it. So this is what's going to happen. That's a lot of talking about. Most of this period, we're going to try to catch ourselves up with the recent material by just hopping straight to how we're accountable for it. We'll try to fill in gaps in between. All right, I'm gonna look in the chat. That's what I'll look in the chat, and I'll show them, and I'll see where we're at. Blah, 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 blah. There's a class. Can you mute? Oh, sorry, mute. Thank you. Great. Can you say it one more time? Wait. Oh, great. Oh, it looks like I'm okay. These questions were like fair, but then it sounds like I actually, like along the way, actually answered some of the questions accidentally. Cool. No, and it looks like people are not unhappy. It looks like you're getting what I'm saying, because I got some sort of happy thank yous in the chat. So okay, good. And look, if you like it, I like that you like it. I'm not saying I'm happy if you're happy. And yes, this is meant to make for more happiness, no doubt. Again, I have a whole philosophy on this. I've been doing this for a long time, and I think, what I like is people to like physics, and it's hard to like something that you think you're sucking at, especially if it's unfair. But when you open this thing in a minute, you'll see it's also hard. So don't think, believe me, I'm not being overly generous. If you get to understand this stuff and you end up getting an A on this material, it is not charity. It's because this material is hard and you can't know it without ultimately knowing it. I'm just trying to help you get there. All right, so but it sounds like people get what I'm saying. Therefore, what blah, blah, blah. Oh, wait. Oh, and if they're private, also everything I'm saying now is to give you a sense, yeah, partly to calm everybody down so they can just do physics, but it's hard enough for me. I try to make decisions based that what's good for a whole group, and that means I'm willing to change my decisions in time if the group changes from semester to semester or condition to condition, blah blah blah. But so that's hard enough. So whatever I announce here in public is like the basic group decision, and like often, as I'm doing now, even if I try to be nice about it, I'm not saying it's a democracy. I'm saying this is the decision I made for the group. Now, there's always individual things that are individual, and especially during this freaking virus, which is affecting everybody very differently, but very much. So please always understand, whatever larger group or decision I make, always, if there's a thing like, oh no, on that day, I personally have to go to it, God forbid, something, I'm very open to hearing those individual things, and those are correctly addressed only individually. I don't have problem having makeup tests for people on, like, I just, logistically, it's hard to manage. So just all those individual concerns, don't think if I made a decision, I can't address them. Yeah, but please do keep them, maybe if you could ask me after class, or keep them in the private chat. Yeah, that's good. Whoever was doing that. I can make exceptions. I just don't want to change a whole rule just for one person. So yeah, or you know what I'm saying. So I think Wait, I'll look in the chat again to make sure. Oh, yes, okay. Right, good. That makes sense. Anybody who's, yeah. And when people have to leave early, I appreciate the way some people, if they leave early, are sort of telling me that, cool, I trust you all, that's good. So I think if this is sort of clear, and again, I think when you open this document, there are going to be moments when you're like, what is this? And again, that always feels that way in physics to some extent. And some extent, it's not fun if it does, but that's why it's happening today. And we've got plenty of time. So, and if I switch you around from breakout room to breakout room, that's just because I just want to scramble it up. You do whatever you want in your room, but you really should use each other to try to get answers, like, and trade phone numbers and blah, 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 if you already didn't in lab. But all right, here we go. We're going to start the breakout rooms in a second.
Quick question.
Sorry. Yeah. Sorry. Yeah.
So since we're going to be doing this all day today, I just wanted to verify, will homework 5 be applicable to this exam as well or no?
Right. Wait, that's a good question. And let me back up for and I be prepared to do this all day, but I think you're right that we're doing this all day, but that may involve me turning back some homework and stuff too. But yes, now homework 5, but interesting about homework 5, if that's what I think it is. Yeah, homework 4 was the mostly reading, right? And you will get 2 things about that. Good question. One way or another, at the least, anything I've assigned you as homework, by the time this exam comes, by the time I get you, for example, solutions to this practice exam, I will also, at the very least, post the solutions to all the homeworks. I think at this point, for example, the solutions to homework 3, we haven't gone over, but I think it's very repetitive of homework 2. So I will post them. That's number 1. Number 2, homework 5 is really and homework 4 was mostly reading, and we talked a lot about it yesterday, but homework 5, very fair question. Homework 5 all of a sudden seems like a nowhere, like what's going on in this homework? It's still about harmonic oscillation, but it looks like a transition. How I'm going to hold you responsible for it, or how we cover it, which is a fair question, or is this: if you look through the practice exam, you will see that one of the 5 problems in the practice exam is literally just lifted from that very homework that we haven't talked about yet. So this is the way we're going to talk about it. In other words, I'm saying right now, actually homework 4, it is on the test because it is harmonic oscillation, and we'll get to it today to see it. So yeah, and you'll see the solutions and stuff. And if I don't get to it, then I'll cross it off. I mean, I will send announcements through the weekend and stuff if I think like, okay, it's my bad, but rest assured, I'll say something like problem 3, you're not responsible for, or something, but I won't add more. As of now, you're responsible for everything. And yes, anybody who really tried homework 5 and is that up to date will have a huge already leg up on thinking about that problem in the exam. To answer somebody else's question, there are 5 problems in the practice exam. Each problem has many parts. They're like big homework assignments. So there's really 5 big parts to this exam. Now, your actual exam won't be that big. That's a lot of big parts. Your exam will probably be more like 3 parts. But as to which of these 5 it is, I don't know, blah, blah, blah. So that's the point. Everything here is fair game. Your actual thing will probably be 3/5 as long, but everything in this 5-part document is fair game. So again, that's the answer to anybody who's asking. But so when I say go to it now, should I even recommend? I know, do it I recommend everybody go to some problem that doesn't have solutions in it. Let me put it that way, because our most productive thing today will be for me to give you solutions you don't have. So do something in there, but don't first go to the ones that already have solutions. That's not a productive use of this time. So I'm creating the group, so I'll look in the chat one more time before I actually. Okay. So when you get that thing that says, please go. Yeah, and I will post, so I will post the homework solutions that I haven't yet. I will before this thing. And how long are you going to be in the breakout rooms today? I would say right now, wait, it's 1:45. This class goes to 3. I think it's fair to assume you're going to be in this segment of rooms. Like I might move you from one to the other, but we'll be in this segment right now, working on our own, at least for 25 minutes. It'll probably end up being more. I mean, to me, it already sounds like a lot, but if you're trying to budget your time, I would say we're all going to be in this group working like this for at least 25 minutes. It might be 40. I am, and don't hold me to that. But yeah, that's probably right. But we certainly don't come back until I see that everybody has gotten into a room. So by the way, again, if you have a second device, if you have a device, if you have a second device, If you have a second device that you're using for whatever reason, I think that's great. I mean, I'm doing that. As long as it works, it works. But if you do, please name that device something that sounds like your name so that I can see that it's linked to you. And then I'll just put those both in the same room and that will solve that problem. Okay, and yes, so I think the rooms are open. If I move you right now, it's just because something was happening. So please go to your room as soon as you're assigned and just, again, just work on the, I hope you're all done. Good, thank you, great, great, great. Hello? Can anybody hear me right now? Can you guys hear me right now? Can you guys hear me? So Kayla, Justin, Xian, Yu, Justin, Xian, Samantha, Yu, Xian, 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 Samantha, Samantha, Xian.
Hey, what did you know me doing? I want you to stop following me. You go. I have to go. I'm gonna plan it. I'm going to know it's going to. I'm going to plan it. So am I. Wow. What's the thing? Okay, get me again. I will do it. Okay, I'm in.
Strawberry banana juice for your lunch? Do you want juice for your lunch? Strawberry banana or both? Okay.
Hello.
Hi, Professor.
Hi. Sorry to
Hi.
take so. Thank you for sending the message. Hi, how's it going? Just get my glasses. But keep to. I start. Yes.
We have a question about part 2 about general hook and question 4. Like it isn't. It's not like a complete thought.
Oh, it might not be. Yes, there may be errors there. Let me look. let me try to get up, but can you maybe read it out loud while I try to get it? You're right, it may be a complete just mistake, but if you could read it out loud while I look for it on my screen.
Yeah. So measured in radians from the vertical, at what angle will we find the mass once? At what angle? What is the particle's approximate speed? Like after once, it doesn't make sense.
Yeah, you're right. No, you're right. Good reading. Yeah, there is an error there. It doesn't make sense. Hold on. Let me just get it. Where did I? Let me get my copy. You're right. There's a word or three missing. Hold on. Okay, here we go. Oh, okay. Yes. Wait, sorry. This part. You picked a good problem to do, by the way. Why can't I? This is part 3. Wait. Sorry. Oh, sorry. Part 2. Okay. So this is page. Tell me, this is page.
Page 6.
Oh yeah, page 6.
Oh yeah, you're right. Oh, that's total garbage. I'm sorry. You're right. The words got all screwed up there. It's supposed to be what the question's actually trying to ask. I'm sorry. I'll tell everybody this. It should just be, you can cross out all the words. You can cross off all the words until it says what is the particle's approximate speed at, like, all it should be asking is what is the particle's approximate speed at t equals 1.33 seconds. And I'm just looking at the other questions now. Does that make sense? Should I say that again? And I'll redistribute this. But yeah, you're totally right.
We should disregard the first sentence.
Yeah, disregard everything. Yeah, everything until it literally starts with the capital W and says, what is the particle's approximate speed? Yes, all that is just like another question that got jumbled into it accidentally. And before I go, and that's great that you caught that. And you picked a good question to work on. And if that means that you're doing okay with the stuff with the couple parts before it, that's good too. But let me just linger here and look for a second that if the other questions, that the other parts still make sense if I say all that. Oh yeah, it tells you that. Okay, good. And it tells you. Oh yeah, okay. Yes. All those questions are. And can I just ask you also, have you gotten up to this in lab yet? Have you done, that's a yes?
Yeah.
We did mass on a spring and simple pendulum as well.
Great. And that's where you did not start the wave.
We're up to wave on a string.
You are,
okay.
We
did 3A, wave on a string, for the video.
Oh, terrific. Okay, and for what it's worth, as long as we're all talking here in this room, I'll say this to everybody, but as long as it's worth, for what it's worth, lab 3, that is not on this exam at all. Like, nothing direct about that is on this exam, but technically this exam covers all the material that you're putting together from lab 1 and 2, which is, why this pendulum is there. So that's good. That sounds like do you guys?
Would it be just chapter 15 in that Halliday textbook?
Right, good point. It's just 15. You'll see today we're going to make a tiny reference to a tiny bit of chapter 13, but right, you're right. It is just what is chapter 16 in that text? Yes, it is just chapter 15. You're absolutely right. This exam is just chapter 15 in the Holiday Resnick text. Yes, and I'll try to say that to everybody too, or feel free to remind me, but yes, that's right. These are good. Any other questions in this room? Or have you oh, sorry, yeah, go.
Real quick, so if for the question we just corrected, the answer on page 8 is in terms of radians, which I feel like no longer makes sense if we're trying to find velocity, right? Or am I mistaken?
No, you are probably right. And in fact, I was worried about that. I didn't catch. You are probably right that whatever answer is there is probably to some other form of the question, and I wouldn't trust it. Yeah, and I'm going to check. So for now, just treat these questions as questions, and right, don't necessarily. I will be starting to make the solutions, and that solution probably just is right, not to be trusted. Good point. What?
In physics, shouldn't we be using radians always instead of degrees?
Yes, you should. Wait, that's a fair question too. And in fact, I especially in like the lecture part of the class, we're really, really, really big on radians for all this stuff. Occasionally, occasionally, if I'm making reference to things that you've done in lab or people are doing for the first time, sometimes I'll use degrees just to make sure that people know what I'm talking about. But you're right. Right? Is there any degrees in this that shouldn't be? Are you noticing degrees in this problem somewhere that there shouldn't be?
Oh, no.
Oh, okay. But yeah, you're right. And yes, you should have your calculator in radian mode when you do this stuff. And like, I would, it's not cheating to be reminded of that or something. But yeah, good point. Um, uh, and I will, but these are good. Good. You guys are good for the moment then. If, wait, how many
Yeah,
people
we're
are
all
in this?
right.
You're good. I mean, it seems like you're very productive. And is everybody, I don't want to embarrass anybody, but everybody who's supposed to be in this room, like like I know 3 people are talking to me right now, but is anybody missing from this room? Like, is Justin here, Grace here, Mariah here?
I think we're all here.
Okay,
Yeah,
so like
Justin's here.
Justin,
I
wait,
don't
is
know
there?
about Justin.
Oh, okay, but Erica is well, oh, by the way, well, okay, I guess I'll move on, but whoever it was that sent me the question or somehow notified me that that was cool. I didn't know that you could do, how did you, like, somehow the computer did single out that there was a question from this breakout room, which
Oh,
actually, yeah, what did you do?
Really?
I did it.
I
Yeah, what did you do? That was great. What did you, how did,
On the bottom of my screen or on like of Zoom, like there's a thing for ask for help.
oh, that's cool. All
And
right.
then
Well,
it says you can invite the host to this breakout room for assistance.
oh, cool. And did I keep you waiting a long, long time or did I?
Not really.
Okay, good. All right, well, this is cool. So I'm going to go to another room for a few minutes, but I'll probably, we won't be in this for the whole class. Like, I'll get everybody together. And so remind me if, these questions you just asked, I would like to answer them for everybody too, if I know. But cool. All right, I will move on. You guys
All right.
are very good people.
See
All
ya.
right. See ya. Hello, Yu, are you there? Yu, are you there? Hi, so you're uh, waiting rooms, joining waiting rooms? No. I mean, we're joining breakout rooms? No, yes.
Sorry, Professor. My phone completely, well, my internet completely lagged out, and then I was kicked out of the breaking room, and I couldn't go back in for like a good 20, 30 minutes, and now I'm back.
Okay, I see. Is there one?
It just wasn't allowing me to get in. It just kept on. It cut off with me. It's my fault. It's my internet issue. It's not anything from your side.
I see. I hear you. Okay, I hear. The only reason I'm getting confused now is there a breakout room assigned to you now? Because I can't find my screen. Hold on a second. I'll try to.
Yeah, I see. Join breakout room.
Oh, okay. So please just do that if you don't. I mean, make sure that works, or let me know if it
Okay.
doesn't work. All right. And Cynthia, same thing. Are you in? Where the breakout rooms go? Cynthia, are you there?
Yeah, my Zoom disconnected. I was in breakout room, but it disconnected.
So I mean, I hear you. I mean, that happens. But do you see right now, is there an assignment to, is it like giving you a button to, wait, I'm trying to fix it too on my side. Is it giving you a button to,
To leave? No.
oh, no, to join a breakout room? Is it assign a
No.
break? No, that's a problem. Hold on a second. Why? Oh, okay, hold on, Cynthia. Ah, okay, yes. It should in a moment. This may be only for a few minutes, I'm not sure, but let me know. It should be saying about breakout
Yeah, I
room.
see it.
Okay, great. So if you could just join that. I mean, again, I don't know how long it'll be for, but that would be great if you could.
Okay. Cool.
Okay, cool. Thank you. Okay. And is you? Is that you? No, you. Okay.
Hi, it my breakout room.
Sorry, say it one more time. Sorry, say it one more time.
It like my connection got lost and I got logged.
Oh, right. Okay. All right. Hold on a second. Okay.
Quick question: how much longer are the breakout rooms?
Actually, I was going to take one last check on one and then shut them down. Actually, I'm going to start talking again in a few moments. Yeah.
Okay.
But so I'm just going to sign you for the moment, just so they're all. Okay. Okay. Thanks. Hi.
Okay.
Hi. Hello. Sorry, I'm interrupting. This is hello. This is Yaverbaum. We're about to probably all gather together, but I just wanted to take a quick. I haven't been through this room. First of all, is everything like okay, technologically and yeah, okay, that's good. And you three, it's Antonio, Alejandra, and Leah. Yes.
Yeah.
And you're all like you're all here. Hello, or someone or Leah? Yes. Okay. All right. And someone, and there's never been a fourth. Someone named you never showed up. Is that correct?
No.
No.
Yes, shut up.
Right.
He didn't.
Right. Okay. Okay. And are you guys fine if you like at a good point for us to all gather together? And I mean, where or do you want to ask anything or check in on anything, or
I'm
you
good.
ready to go? You're good. Okay.
Yeah.
All right. If there's no crises in here or anything, this is just like a warning that we're all going to gather together, and you've all everybody in this room has gotten back homework 1 and homework 2, I think. Yes.
Yeah.
Yes.
Okay, cool. All right, thank you. I will leave you. Okay. Wow, so fast. All right, maybe that was too much time. I don't know. All right, well, let's see. Hello. Okay, it looks like okay, we're all here, I think. Okay. All right. Obviously there's many different ways to use class time in general, and then it's all a different set of options when class is electronic. When you guys are all just doing stuff is the time that it seems like, or it could be potentially the time where I'm doing the least, or potentially could be the time that requires the least of me. But so it's very hard often. I mean, it's very hard for a professor to like stay quiet, but the truth is nothing is ever as productive as just like you guys having time to work. I mean, if you take advantage of it. So I hope people did. I mean, in any breakout room, of course, at any moment, if you just want the quiet time to think and do stuff, I'm a big fan of quiet time to think. But I do know, for whatever it's worth, my philosophy on tests and cheating, you'll see more and more just through the fact of when you take your test and you get your grade and everything. But physics kicked my butt through college, through graduate school twice. I loved it for 1,000 reasons, but never because it was easy. But we had a lot of crazy take-home exams like this when I was an undergrad. And what's my point? They're a recognition of many things, not the least of which is nobody really does science really alone. Nobody can do science, especially physics. Nobody does alone. In the final moments of physics, you're always alone, but everybody helps their one another through like navigating the universe. I never could have gotten through college by myself without a lab partner, stuff like that. Even the lab partners I hated, but blah blah blah. So I hope you traded phone numbers and stuff like that while you're in there. All right, but I went around. I want to first address any questions that I already got that I can remember that seemed worthwhile, and then say some things and take questions. Again, I will be posting solutions to this over time over the weekend. I'll be posting updates and revisions as well, and probably point values just to give you perspective. But first of all, yes, in the pendulum problem, which is related to lab 2, the pendulum problem, which is someone might have to remind me. I think it's part 2 of the exam. Some of you chose to start on it, some of you didn't. Just please go to that for a moment, that pendulum problem, and maybe someone can confirm. I believe it's part 2. Question lower 4 or something like that is incoherent. There's a huge typo in the middle of one of the questions where like 3 questions got jammed together and end up making no sense. It's hard for me to pull up these different screens, but someone can remind me. If you see a question there that looks incoherent, yes, cross out all the words entirely until it says, what is the speed of the pendulum bob at approximately 1.33 seconds into its motion or something like that. That's what the question is supposed to be. Just find the instantaneous speed of, I gotta find it here. Yeah, so this is part 2, general hook. And it's question Roman numeral lowercase 4. There's all these words that just shouldn't be there. It should just say, what is the particle's approximate speed at 1.33 seconds? And some answers do happen to be scrolled into this question for your benefit, but if you find an answer or solution to that question, it may very well be to the jumbled version of it. So don't trust the answer to it yet. I will post, just trust that that's the question. That's one good thing that somebody pointed out. Then this whole huge table of values and everything that's in the long, overly written problem number 3. I mean, that's an important problem because it is trying to show you again how these harmonic oscillations just come up anywhere and everywhere in nature from data. And then once you know that they come up, you know what to do with the math. So, but there's a lot of writing in that. It is not asking you to fill in those tables of values. It's showing you the tables of values to show you how this was generated and make it real. But you are not being asked to fill in those tables. That's on that. Okay, on problem 4, part 4, simple harmonic heck, which is entirely identical to the homework that you were just recently assigned. So nothing new. It's exactly that homework, and I'm just saying, this is my way of saying, yeah, you do need to know that for the exam, even if you end up sort of learning it through the solutions to this practice exam. However, I will start talking about it today. That problem, number 4, simple harmonic heck, what seems weird about it is that all of a sudden it's talking about gravity, which we haven't talked about much in class, the universal force of gravity, GMM over R squared. Now, the truth is you really technically have seen that, or I mean, in principle, have seen it or have some comfort with it from physics 1, but even if you don't, the real truth is at this point, we're believing if someone just tells you what a force looks like, if you know F net equals ma, you know what forces do to objects and you know how to deal with it as a physicist. So this problem is sort of reintroducing us to the force of gravity. It doesn't matter really how much you remember about it or how much you don't as far as approaching this, but it is asserting, and this I'm going to start writing something in a second. This everybody needs to know. This problem, which again, to be clear, is homework 4. So however you want to think about this in terms of going over notes and stuff, I want to break down this problem 4 for you a little bit right now. It is reminding you about gravity, that gravity is a force that seems to exist between any and every pair of point masses in the universe, right? Every point mass exerts a force on every other point mass. It's telling you how that force of gravity as a magnitude and a direction depend on the independent variables just mentioned. Okay, but then it's telling you something a little bit more specific, a little bit more specific about gravity, which you may not have had occasion to think about in physics 203, and which is a bit of a something to just take on faith right at this moment, but then we're going to develop and prove a little bit later on. Let me tell you, so there's two statements. Let me say this again. I'm going to start writing this down on a whiteboard in a second. So you could consider this teaching or reviewing or whatever, but problem 4 in the practice exam, which is in effect homework 4, all of which will be in the real exam. It is setting up a situation involving gravity, and it's making two assumptions about gravity that you are being asked to accept, understand, and take on faith at the moment. Like, understand means know what it would mean to apply them, whether or not you're suspending belief in them. So this is what I'm about to write down. This is the thing you would not necessarily expect just walking into this class. I'm almost there writing it. Okay. And again, anybody who tunes in right now can interrupt and say, wait, what are you talking about again? Because I do feel like it's possible you wouldn't know why I'm doing this. I'm saying.
So what homework question are you referring to?
Right. Great question. So I'm referring to, I believe, the very part 1, the very first page of, I believe it's homework. Oh, I'm sorry. I keep saying homework 4. That's a problem. I believe it's homework. I'm sorry. I mean to say homework 5. The homework that, like, you'll see the fonts look the same in everything. If someone could confirm this, I've been saying homework 4, but you're right. I think that's what the confusion is. I mean the very most recent homework, the homework that's called covert oscillations or something like that. And you'll see why it's called that. So there's a homework assignment called covert oscillations or something. I think it's homework 5, where once you look at, and again, I'm telling everybody, even if you never opened it yet, even if you're behind, this is not a secret way for me to find out who's behind on the homework. I don't care, like, because I'm behind too. Even if you never looked at it, if you look at it now, you'll see a problem all written in the same font and everything as this business about unspringy springs and the gravitational tunnel, aka subway line 42. Can anybody confirm what I'm talking about here?
That's homework 5.
5, okay, thank you. All right, so sorry, so homework 5, yes. But so good question. Just so that I'm simultaneously right now about to address this homework. In effect, I'm about to quickly go over this homework, if you like, or at least start it. And do this problem in the exam, because so good. So let me just get the notes open. No, sorry. I'm trying to be a little more careful about the notes now if I'm going to post them. Hold on, let me just so you know what it is when I'm doing it. Okay, so and everything I'm about to say too might help you a little bit also for the very last part in the whole practice exam, which is also looks at it. All right, this is what I'm saying here. Homework number 5. Oh wait, can you see my screen? Can you see? Am I sharing the screen prop? Can you see a whiteboard that says
Yeah.
Yes.
Yeah.
All right, great, thank you. All right, so this is homework number 5. This is also pre-midterm, practice midterm. Okay, this is all, in other words, the issue of the gravitational tunnel, which I'm in effect introducing right now for the first time. Okay, what is it based on? First of all, it's assuming something like this, right? It's assuming, it's assuming that somewhere in physics 1 or physics 203 or whatever, you got acquainted with something that looks something like this. Maybe you had a D in the denominator or whatever, but that there's throughout the universe, any given two masses, point mass 1 and point mass 2, separated by distance r, will exert equal and opposite forces on each other, whose magnitude is determined by this expression, right? And it's assumed that G is a constant, which is also universal, which you don't have to memorize, but you should understand that it's really, really tiny, and that it's there. Its only significance is to make all the units work out. That is, if we didn't insist on measuring in meters, kilograms, and seconds, we wouldn't even need this constant at all. but it's there just to adjust everything and leave us so that this force is actually measured in newtons. So I'm saying this very quickly, like in principle, you know this from physics 203. Now, I actually can say a lot more about this, whether you do remember it or not. In fact, not to be cheeky, but there is a lecture posted already from last semester where I like in detail remind everybody how gravity works and all of that. And I would ask you to check that out. It's somewhere in this Vimeo collection. Please check that out if you want reminders or refreshers on gravity. But I'm saying there is gravity in the world. I'm now starting to say, as a more advanced physics class, that, okay, gravity is a force. It is a force. All forces are vectors. So all vectors have magnitude and direction that we often want to keep track of. In the case of gravity, it does start to become important, taking into account its direction. There are subtleties. So this whole thing that I just wrote down from physics 1 is really, that's really just an expression of how the magnitude of the force vector works. I want to be a little bit more clear and explicit and careful about its vector nature. So with our new notation in this class that we are responsible for on the exam, if it's new to you, I'm going to say, all right, there's a force of gravity, okay, a force of gravity, which is a vector, and any vector, remember, can be viewed as a simple product, a monomial of a pure magnitude times a pure direction, like some kind of unit vector, right? Well, I'm going to say, sure, gravity is a vector that can be written that way. Here's everything in the parentheses, all the constants multiplied by together and divided in the parentheses represents the magnitude of the force vector called gravitational, that one big mass called m1 will exert on some smaller mass m2, right? Everything in the parentheses is the magnitude of that force, and that force is always going to point in a particular direction. What is that direction? Well, the easiest thing, what I want to say, what I know about it, what's important is if I'm assuming that there are these two mass points, one really big and one small in terms of mass, right? Just because they might be equal, but there's no reason to assume that. And they're both equal in volume because they're both points. If I have these two mass points, if they're separated by some distance r, I think the more precise, careful way to look at it is, let's say that they're separated by the displacement r, like the vector r, where r is a vector, right, that points very specifically from one mass to the other. Well, which one to which? Well, of course, in a way, it's all arbitrary. I mean, multiplication is commutative. But let's say if you're focusing on the gravitational force exerted by some mass 1 onto some mass 2, and if we're being arbitrary, but we're being consistent. So let's just in our mind assume that mass 1 is the bigger of the two, right? Again, if they could be equal, but that would be a special case. So we don't want to start with a special case. So assuming two random masses, if m1 refers to the bigger one, and m2 refers to the smaller one. And let's say what we want to know is the gravitational force exerted by m1 acting on m2, like as opposed to its Newton's third law, like flip reaction, right? So I'm example looking at the gravitational force exerted by the sun onto the earth. I'm going to declare here now, to be clear, that there's this vector called r, which is a displacement from m1 to m2, that is, r specifically points from the actor to the actee, like from the source of the gravitation to the receiver. In this case, let's say that r points from the sun to the earth, for example. Now, again, I know in the other side of my brain that, of course, the earth also exerts an equal and opposite force of gravity onto the sun. That's true. But when I'm looking at that, I would draw an arrow in the other way and say, oh, then r points from the earth to the sun. But whatever designation I'm making, if I'm looking at the sun's pull on the earth, I draw an r vector that points, that isn't just distance now, it's displacement, and specifically points from m1 to m2. Then by our new definition and notation, right, r is like a radial vector. It points from one place to the other. I don't know what it has to do with, it's not aligned to any axis of space x, y, or z. It's aligned to the way these two objects are aligned. But by definition, r hat would then equal the length of this vector. Would equal this vector itself divided by its own length, right? This is by definition of any unit vector. In other words, the unit vector would be that arrow that designates here, that tells us what it would need to go from M1 to M2 from the source to the recipient. So in other words, I'm going to put that, I'm going to make use of that and say that this is where unit vectors start to come into play. The proper way to say the law of gravity is that there's a force vector which has a magnitude given by all those numbers in parentheses, but which has a direction that, according to this expression, points negatively, like I'm putting in a negative sign. It points negatively. What do I mean? I mean, if the force of gravity exerted by M1 onto M2, according to this notation, notation introduced so that we can precisely track direction as easily as magnitude. According to this, it says that the force of gravity exerted by the sun onto the earth, in order to know its direction, I would look at an arrow pointing from sun to earth, and I would note the negative sign and thereby flip the arrow, right? In other words, the direction of the force of gravity. The direction of the force of gravity evidently points in the opposite direction from R necessarily. If R points from the sun to the earth, then the gravitational force exerted by the sun points back toward the sun. What do I mean? In other words, it's a pull. Like, what I'm saying a lot right now about something very technical, but something that's going to become powerful for us. By using this unit vector notation, by throwing an R hat in this expression, what I'm now doing is making the entire right side an actual vector. And it's a vector which necessarily points against the displacement vector from M1 to M2 and has a magnitude like scaled down according to that fraction inside. If you follow the notation I'm saying, it means like the expression for gravity will always have a negative sign there, because negative in effect, if you accept this just as a piece of notation to keep track of things, but if you use it the way I'm using it, then this negative ends up necessarily, for any force like this, any what we would call a central or radial force, like between any two particles, having that negative there necessarily means that however I look at this, I could look at M1 acting on M2, or I could flip the whole thing and look at M2 acting on M1. What I'll always get is that what one thing does to the other is it yanks toward itself. This is always a pull force, a force of attraction, that is made explicit and demanded explicitly by the negative sign. Why am I making such a big stink about this? Because of course, where we're going to build from this reminder of gravity is we're soon going to build, or like the Coulomb force for electricity, electrostatics, which mathematically looks identical to this. Like any math we could pull from gravity, we're going to use for electricity. And we're going to see in electricity, as you know from chemistry, protons can pull electrons, and it turns out that they do, just the way masses pull on each other. But of course, protons can push on protons, and electrons can push on electrons. All that is embodied in one clean vector statement, as long as we use the R hat and then recognize that if there were ever a plus in front of the whole thing, then that would mean a force pointing along the direction of R hat, i.e. a repulsion or a push. Okay, from here on in, I'm saying when you see negative in an inverse R squared force, it means pull. If you see a positive, it means push. Okay, and from here on in, the unit vector that's sitting there is not another number to multiply. Like that R hat is telling me that the whole right side is a vector and it's telling me its direction. But literally the magnitude of R hat is by definition 1, like based on our lecture 2 days ago. So it's intentionally placed there so as not to mess with the magnitude of what's in the parentheses. Okay, I'm sort of saying this fast, but I'm saying from here on, when I think of gravity, okay, from here on, I think the law of gravity says this. I'm just rewriting the same thing. I think of the law of gravity as a vector, and the assumption is that the situation it's discussing is something like this. Okay, that's what I believe how gravity works, and we're going to use it. But then now, the problem 4 also starts to say some stuff that we are actually going to prove, that we do care about. It's not a throwaway. And there's lots of arguments and stuff for this. In chapter 13, which you're not responsible for the exam, but like there's some discussion of gravity in chapter 13 that you can look at of the Holiday Resnick textbook if you have it. But it amounts to 2 claims that for right now, for exam purposes, to keep our heads clean, I want, if you can see it all how they might be true, then just accept them as true for the sake of argument for now. And believe me, we will demonstrate and prove that the 2 claims, okay, the 2 the two implications, the two, sorry, I'll say the two implied or derived claims about gravity that we're just going to, from here on in, or for the moment, use. Claim 1. Okay, in fact, I'm gonna give you two claims that actually both have this same given. I'm sorry, so this isn't even claim 1 yet. This is the given that's gonna apply to both of the claims. So here we go. But the given that you're gonna picture for these claims is a spherically symmetric mass shell. What am I getting at? Well, let's go back for a second. GMM over R squared, what it's really saying, and it's an astounding claim, the universal gravitation claim, but it is a law, GMM over R squared, that is. It's a law telling us something about mass points, right? M1 and M2 are assumed in that equation to be infinitesimal volumes of mass, right? Like, it's just dots of mass that can differ only in how many kilograms are actually packed into those little dots. So what's universal about that law is it tells us how, given any two bits of stuff in the universe, any pair of mass, automatically they apparently attract each other automatically according to that law, and then therefore everything in the universe is attracted according to that law. Like, but what it is, why it's everything, is because it's a law that only can handle one pair of bits at a time. It's a law about point masses. It doesn't say anything actually about a ball of mass like a basketball or a baseball or God forbid, or some atom or a planet. Like, the law of gravity is not about planets and suns or stars or comets or anything. It's about bits, points. What I'm going to say I'm going to say, let's picture something that is much more realistic than that, but still has that simplicity. Let's try to apply gravity to the actual world and assume that instead of having a bit of mass in front of you, assume you had, in fact, some big round thing, like an orange or a basketball. In fact, a huge collection of little mass points. Let's assume you had a continuous collection, a continuous distribution, a smear of mass points that all amounted to some big size thing, like a basketball. Right? Assume it was really, really round, like spherically symmetric. That is, that all points on the surface really are equidistant from some center. Oh, someone's coming in, excuse me. Okay, assume that, which is still simplistic, but not as simplistic as some point mass, right? Assume you have a spherically symmetric, now I'm gonna say, so the negative means a repel. Yes, negative, sorry, I'm just seeing the chat, sorry. Yes, negative sign means attractive force. Right, and positive means repelling force. From now on, I'll say it again, but anytime in the case of R squared forces, like between electrons, yes, sorry, that's just a chat aside. So assume that you have some spherically symmetric object, like you could picture a sphere, but more specifically than that, picture an object that it doesn't even have to be a solid sphere. Like, it doesn't have to be it could be like a golf ball or a soccer ball, where it could be hollow on the inside. That I'll even allow that complexity, right? Like, we're not demanding some uniformly dense thing, but if it's hollow inside, the hollowness has to be symmetric, right? So we're assuming some kind of shell, some kind of thick outer rim of some, like, picture that in your mind. It's like the one level closer to reality that we can get for the moment that still has the simplicity of a point. I'm going to say that if you picture a spherically symmetric shell, so like this, if you picture, which explicitly the law of gravity never says anything about, but if you picture something like, right, a shell, so like a sphere with a spherically symmetric cavity cut out of it. Claim 1 is that if you are any particle separated at some distance, lowercase, some displacement, lowercase r, from the center of this shell, right? So if we no longer have a point, but we have a spherical shell, if some other little point of mass, some small point particle M2 is a displacement r away from the center of that thing, then just as you might expect, and just as you've probably been tacitly assuming since day one of physics 203 or since 6th grade, just as you would hope and expect, it turns out, yes, if r is greater than capital R, if you are outside that shell, if your displacement from its center is greater than the radius of the shell itself, if R is greater than R, then in effect, then, and only then, I can write the same equation I did in the back screen, and I'm writing the exact same thing again, but what's the content? What does that mean? I'm saying if you're outside a spherically symmetric shell, just as you've probably always believed in your life, then all the gravity, the total gravity of that whole shell will all add up together to treat you being particle M2, to treat you as though there was just one big, huge amount of mass all located at the center. Right? In other words, all the law, it's just what you probably always believed, that all the mass of the sun pulls on Earth as though there was just one monstrosity of whatever it is, 5 times 10 to the 31 kilograms worth of mass, all located this incredibly dense, almost like black hole-y kind of point at the center of the sun, that we believe all the gravity, or the Earth, we all act like all the gravity is coming out of the center point of the Earth. We're acting as though all of its mass is just concentrated there at the center. Well, it turns out, yes, we've been getting away with that, and it turns out it is fair to do that, but you have to realize that there is something that we're getting away with that somewhere has to be justified. In other words, Earth, I mean, any big round thing is a collection of small things. It turns out the sum total gravity of all those tiny things all being collected does all add up nicely and symmetrically the way you'd like, as long as the big shape is symmetric that way. But I just have to say that that's true, and you can assume that for the homework, and we'll prove it later. But then I'm going to say one more thing that's harder. But wait, first, there's a question from someone. Sorry, or are you losing the audio or something? Sorry, question. Wait, question? No, I thought someone had a question. Okay, well, I'll go. If not, so claim 1 is kind of like maybe what you already think, but I'm just pointing out it is a claim. But claim 2, a little bit less a little more counterintuitive. Claim 2 is if you still assume that same spherical shell of mass, but if you now assume this, in other words, if now we have that same big mass, so this is this big spherical shell of mass, and it's of radius capital R. If we assume now that you're at some location that this is all M1, and you're some little particle called M2, and you're at some arbitrary location, some variable displacement R from the center of this thing, just as you were before. But here, this time, the distance of you away from it is smaller than the radius of the whole given shell. In other words, if you're inside the cavity of the shell somewhere, if you're within the hollowed out cavity, the vacuum of some spherically symmetric cell, what it turns out is, and again, we are actually going to prove this, and we're going to look at this a number of different ways, but for right now I'm saying it, it turns out that the net gravitational, I'll write this in a different color, the net gravitational force on you, the particle M2, the sum total gravitational pull from all the little bits around you, that all ends up summing to 0 in this case. So I'm going to say one more. In other words, I'm going to go back a page a second. I'm going to flip-flop between these 2 pages for a moment. I'm saying, given some shell that's round, if you're outside that shell, the shell acts just like you'd think. It acts just like there was a point, a really, really heavy point at the center of that shell, and that point pulls on you, pulls on you towards the center with the expected force of GMM over R squared. But I'm saying if you then go in, and that's because, I mean, what's really happening is every little bit of the shell is its own little bit of mass, right? Each one is pulling on you, like this little bit is pulling you that, this little bit here is pulling you that way, but then this little bit is pulling you that way. Sorry, you are here, you are here. You're being pulled by this bit this way. You're being pulled also by this bit that way. You're being pulled by this bit that way. So there's all these cancellations and reinforcements of all these little bits. If you're outside, it turns out they all nicely add up to exactly what you expect. It all acts as though you're just being pulled to the center of all this. But if you're already inside, if you're somewhere inside in the empty space, I'm saying what turns out to be true is all these bits add up in a funny way where they don't all reinforce each other. They all end up canceling each other out and pulling you not at all. If you're anywhere in the cavity of a spherically symmetric mass shell, not that this would ever happen, but if you are everywhere inside that cavity, it's weightless. You're weightless. Your weight is zero. It's a Newton's first law machine. It's just like a three-dimensional ice skating or air hockey, pond where you just like caroom around, banging off walls to walls, always maintaining your constant speed. I'm not saying this would happen, but I'm saying from this knowledge, we answer problems about things that really do happen. So the two cases I want you to get is if you're outside a spherical shell, the whole shell acts like a point located at the center. You can use that whenever necessary. If you're inside a shell, the whole thing adds up to zero. What the problem is asking you here, I'm going to take a breath in a second, but I may end up walking through this problem today and that'd be fine. The problem at hand, the homework problem number 5, the review problem, the problem is saying, okay, given all of that, given that big mouthful, here's just a out of nowhere application of gravity question. It seems like it's asking you in the problem. The problem is, what if you have a solid sphere, like plum pudding, so to speak, like the way that, what if we have this whole sphere that's actually solid throughout mass 1? In fact, like how solid is it? This is how, oh, sorry, if I'm outside there. I'll look in the chats in a second. I'm sorry, I will look in the chats in a second. But let's say you actually have a solid thing, which again is just one step closer to reality. That's always what we're trying to do in physics. We just start with what we know and build the pieces till get to what we want to know. But if we have a solid sphere, let's say this solid, let's say so solid that it's uniformly dense, right? Solid, 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 not like more thick over here and less thick over there and then nothingness over there. Let's say it's solid, like the mass per volume, let's say, like for any given bit of volume, you have like for any given cubic centimeter, you find, let's say, a kilogram of dirt. Then in 2 cubic centimeters of space, we're going to expect to find 2 kilograms of dirt. Like, let's assume the density is, in other words, a constant. Let's give that constant a name. In fact, I'm going to call it, that's supposed to be a lowercase rho, the Greek letter rho. It's like sort of an R. It's sort of a phi put together or something. From now on, the 3-dimensional density of something, I'm going to call rho. In this case, the mass per unit volume, or when we get to electricity, like charge per unit volume. If I'm talking about a 3-dimensional density, I call it rho from now on. Note that's a triple equal sign. And I'm going to say, let's assume that for this problem, rho is a constant, right? You see my notation? This is just a fancy way of saying, let's assume that there's a density, which we're going to designate rho, just because that's what people do. And let's assume that density doesn't change. So this thing is thick, solid, right? And by the way, as just for notation aside, sidebar, because this is going to come up, like in physics, density is stuff per space, right? Stuff per space, but space can come in any dimensionality. Like when we're talking about, if we're talking in physics about the amount of stuff per 1-dimensional space, per length, that is, we usually use a lambda, or sometimes we use a mu. Either way, that is 1-dimensional density. Okay, this comes up with like the density of charge in a wire in a circuit or something. Then if we're talking about, this is a sidebar, but if we're talking about amount of stuff per area, like 2D density, we usually use lowercase sigma to designate that. Here in this case, we're using lowercase rho to designate a 3-dimensional density. so that was all sidebar, a three-dimensional density of mass per unit volume. So we're going to assume, oh, someone's in the waiting room, okay. We're going to assume that we got this big, we're getting closer to something that like looks, that we could think of as the Earth or the sun. We got this big ball in our mind, solid with mass throughout. Like, you know, any given bit of volume of it that we pick, we find an amount of mass that is equal to any other given equal bit of volume in the thing. And the question here, again, the homework question or the test exam question is, given this solid sphere, where the rho is given as a constant, the total mass is a constant, and the actual constant radius of the whole thing is a constant, we're asked in this problem to derive the net gravitational force of gravity on some particle. Sorry. We're asked to get the net force of gravity of some particle located some variable displacement from the center of this thing, say whether inside or without. Like, please note my notation. I use capital R tend to try to use capital letters to mean constants, or I use letters from the beginning of the alphabet to mean constants. I use letters from the end of the alphabet as lowercase to mean variables. So there's going to be a lot of R's and R's floating around here. Capital R means the given constant size of this thing that we're talking about. In this case, the radius of this solid sphere that is actually fixed and given. Lowercase r is the independent variable, right? Lowercase r stands for how far some second particle is from the center of this big solid constant r. So again, lowercase r is a variable, capital R is the constant. The question here is, if you are some particle, right? If you are some particle, M2, sitting around at some location, lowercase r, located r away from the center of the solid sphere, what this question is asking is, well, what's the force of gravity doing on you there? Like, how does it depend on your distance? Like, if you're closer to the center, are you heavier or are you lighter? And just like, you know, if you're farther away from the Earth, you're lighter. And if you're closer to the Earth when you're outside it, you're heavier. It's asking that kind of question here. What's the gravity function doing? How is it varying from spot to spot if we're inside a solid sphere? Inside a solid sphere. Now, I claim that's a question that has not been asked. You might have seen it in your life. But let me be clear, it's not asked in Physics 203. Like, this is not old news. We're asking, if you really get that, the one thing to get about gravity is it's the effect of one particle, one tiny point on any other. If we're now in this whole continuous mess of particles, this plum pudding solid sphere, and we're somewhere inside it, so everything is pulling on me from all directions, but they're all adding up, superposition, to some net force. I want to know what that net force is doing to me inside. And that's the question. I am going to, wait, what time is it? Okay. I'm not saying I'm not going to answer it, but like, that's the question. In theory, you were supposed to think about it on your own for homework, which just means in theory, it's figure outable. I'm not saying this is easy, but it's not like I'm expecting anybody to have to pull out some new or arbitrary knowledge from some other black magic bag. Like, somehow we can figure this out, and it's not obvious. It's not GMM over R squared again. Like, that's the force between 2 points. But also, weirdly, this has something to do with all the material. I mean, I'm seemingly asking this out of nowhere, so that's unfortunate. But the reason is that once I find the answer, it turns out this does have a lot to do with the material we're doing now. So, I mean, it's not really out of nowhere. But I'm just like the last few days, I'm looking for a function. I'm not looking to plug into a function and get numbers. I'm looking for a function. I'm looking for a function. I want a function that is like it'll be like this. Like, here's a function of r, f equals gmm over r squared. It's telling you that r is the independent variable, m's are constants. If you plug into r a certain number, it'll spit out a certain number for your force. That's the kind of thing I'm looking for, some function of r. But I don't think it's going to be exactly this, because I think you're sitting, yeah, it's asking for FGR, right. I'm looking for FGR as a function of r, absolutely. And the symbol for 2D density is supposed to be a lowercase sigma. for 2D density, it's supposed to be a lowercase sigma, like this. For one-dimensional density, it's supposed to be this or this. And for three-dimensional density is rho like that. I mean, my handwriting is bad, but yeah. Right. So we're looking for, again, this is the new question. Where even if you thought about it last night, like I haven't answered it yet. We're looking for how gravity behaves, how it varies from spot to spot if you're actually inside the Earth. Does anybody have any thoughts? I mean, I obviously I can do this, but has anybody had a chance to look at this either in their breakout rooms or for their? If you haven't, then this is the best use of your time because but if you have, please. Yes. Okay. Yes. Good.
Yeah, one thing like that helped me because I was confused for a second was if you do small m over little v equals big M over
Yes.
big V, you can get a really good substitution from that.
Awesome. All right. So this man said yes, and in fact, and I'm going to exactly do that. Should I even? The thing that's going through my mind is, oh, I wonder. You can get a good substitution. Substitution for what? I might be wondering if I were, but yes. So the first thing he says, Antonio is saying, is, look, the density is constant throughout this thing. That's an important piece of information. That means for any one little volume you choose, the ratio of mass found in it to it must be the same as for any other volume you choose, he's saying. And I agree. Oh, I guess I'm going to ask now. I totally, well, I guess I can go one step further. In other words, the volume of a sphere, what is it? Yeah, by Antonio, if you don't mind, like what is the volume of a sphere?
It's 4/3 pi r squared. So in this case, 4/3 pi r1 squared, I guess. Or no, pi r cubed. My bad.
Nice. Yeah, no, you're good to say yes. Saved it before yes, absolutely, because it's three-dimensional. Its volume has to be r cubed, and so he's saying exactly this. I totally agree. Like, and this is, by the way, this is what I mean that I would do on an exam. Like many people who are writing this down right now might even not know quite where he's going with this or I'm going with this. Maybe even when he wrote it down, he didn't totally know where he was going either. But the thing is, this is the advantage of starting with things that are true and then trying to make them relevant. This is all right, no matter where it goes. This is just all correct. Now, it starts to make the question more and more clear, like what's he doing with this or why? It starts to show, like he said, Antonio said, you can make a good substitution with this, meaning given our knowledge of the entire mass, we might be able to use this to to write out an expression of known constants to describe some unknown relevant part of the mass. Like we can use this to re-express, in other words, this all means that M2 equals I think. Yeah. Right. Yeah. This is just sloppy, but he is saying, look, if you're interested in some other piece of some portion of this whole mass, whatever portion you find, well, it will be in proportion to the original mass in the same way that how far out you are is in proportion to how far out in total you could go for the whole mass, except by cubes. In other words, if you stand halfway from the center of this thing, if you're standing at a position R, that if R is halfway out from the center to the edge, what this is saying is then right? I think I sort of did that fast, but like the point is, if where you're, or I just did it backward. I'm trying to go too fast. I'm saying if you, I'm making this more complicated, but I totally agree with him. If you stand halfway out to the edge of the whole sphere, under your feet, you're encompassing a mass that is not 1/2 of the total mass of the whole thing, but 1/8 of the whole thing, because this is three-dimensional and a mass is directly proportional to the cube of distance to the volume. Now, I agree with all this. The question is why? I don't know if Antonio wants to answer this or somebody else, but like if I do all this, what I guess I am asking Antonio if he wants. What do you mean by M2? Or what good is this? Like what does M2 refer to, or what mass am I getting that I can substitute from all of this?
Yeah, so the substitution that for me was useful is if you go back to the force of gravity equation, where you
Right.
have M1 and M2, now you substitute in M1 for what you got there.
Yes.
And so it'll start canceling things out that are really convenient.
And why I totally agree, and I'm exactly going to do that. And to everybody, I'm just looking at the magnitudes. I think I'm not even worried about the directions for the moment. I'm going to do exactly what he said. I don't know. Well, yeah, I'm going to do exactly what he said. The question is, why is it fair? Why is it fair? Or a question might be, why is it fair? Or why is it he? In other words, this. Let's do this. Let's do this. Let's be very clear. Ooh, did the audio just cut out? Did something just cut out? Oh. If this stands for what we just got, if this is what we're doing, if we're going to, I don't know, did the audio just cut? My audio, could someone say something?
Yeah, we can still hear you.
Oh, okay, thank you. All right, so see the twos and the ones start to get can get very confusing here for a moment. I'll stop even before. What I want to say is, we're looking at the gravitational force that this entire solid sphere is going to exert. The entire solid sphere M1 is going to exert on some little particle M2 somewhere trapped within it. The substitution we're about to make that Antonio is recommending actually suggests that there's a third mass of our consideration. Like the thing that we're gonna, if M1 used to mean the whole solid sphere, but now we're gonna do this whole thing, and we should, that Antonio just said, it means M1 is no longer gonna stand for the whole sphere. M1 apparently is going to stand for the entire mass of the, what you might call, subplanet, or the inner planet, or something like that. In other words, if you look at what, if by R1 and R2, if by R1 we mean the given radius of this whole thing, of the whole solid sphere, but if by R2 what we mean is like where we're standing in the sphere, the variable R, then what Antonio is really saying is that what we can figure out is the mass of entire subsphere from 0 to lowercase r, like the sphere from to lowercase r, rather than, which is like imaginary or it's hypothetical. Instead of talking about, we already know the mass of the whole sphere out to capital R, but if we imagine ourselves standing at any variable position lowercase r, then that means we're standing somewhere within the innards of this sphere. And that means you can imagine drawing a line from below your feet all the way to the center. And that line from your feet to the center is like this inner planet that you're standing on. And while you're sandwiched between that and a big shell that goes over your head, right? I mean, I don't know why we'd think of this at all, except that it's totally the right thing to do. But literally, then specifically, like we were given this whole thing, M, which is supposed to be some big sort of planet, and its radius R. But if we're standing here at lowercase r, then even though there is mass everywhere, what Antonio's doing, and everybody else and anybody else who did something like this, they're saying, you wait, we can stop and consider this mass here below our feet. We'll call that M star, if you like, or M1 star, and M star has to be to as the total M is to the total, right? I am just rewriting what Antonio said, only I'm just adjusting some of the variable names or whatever to make it clear what they mean here. Like what he already did, the 4/3 and the pi's cancel out. But now what I'm saying is, okay, and the mass of that subplanet equals the original mass times this fraction, just simply the fraction of the radii cubed. And if it now, in a moment, when I make that substitution, as we're all going to do, what I'm doing by making that substitution is in effect getting the total gravitational force that's exerted from the inner subplanet. It's not taking into account anything above my head, but it totally will take into account anything below my feet because of claim 1 that we already established, that if you're outside some planet, the whole thing acts like it's located at the center. So yes, like the total gravitational force exerted by that inner thing is onto any small particle is this. I'm just looking at magnitudes again. So like Antonio said, I substitute in. So let's sub in. And all this is possible only because we had an expression for the density that allowed this to be done. But we're going to say right, people see what I'm doing? I'm, like he said, I'm just subbing in. I'm subbing in this, gross, but that's what I'm doing. So that I'm getting this, so that he's getting, we're getting, oh, and I'm not even looking at the negative sign for, well, no, I'll keep the, I mean, there's always that negative sign because it's attractive. It's so attractive. Because it's attractive, there's a negative sign. So I'm now saying this, again, this original M is the original M, the thing that we knew something about. But now we got R cubed down there. We've got R cubed in the numerator and R squared in the denominator, both the same R's, both the same lowercase variable R. So there is a cancellation there, leaving us with just one lowercase r in the numerator, a capital R in the denominator. Like that's different, that's unusual. This is just about to be an answer. We're actually, again, we're almost actually done. Oh, which is good. And there's no star. There's like a star on my left side. I mean, an asterisk on my left side of this expression, but there's no asterisk on the right side. So I'm trying to emphasize that I did what Antonio said. I don't mean to keep, but what we did was what we said we were going to do. We got a new expression for M for this subplanet and just decided to assess the gravitational force exerted by all of it. And that's what we have here. But why is that helpful, or why is that even a final answer? The question was asking us to get the total gravitational, it was asking us to get the total gravitational force felt by somebody trapped here between, like somebody's in the middle of the plum pudding. What we're in effect saying is if that you're anywhere in the plum pudding, then you are sandwiched between two bodies. You are standing on top of some smaller inner subplanet, which we just did a calculation. And above your head, there is this whole shell, like right above your head, there's a whole sphere with like a donut instead of a pastry. There's all the mass above your head that's there. And we didn't say anything about that in our entire calculation, but I'm just to jump to the chase. And I think this is what Antonio and his group were assuming correctly, or inferring. We had two claims at the beginning of this class. One was that if you're outside some spherically symmetric thing, then all the gravity pulls on you as though from the center. And if you're inside some gravitationally symmetric thing, then all the mass adds up and does nothing to you, right? So what I'm actually saying here, if you're inside a solid sphere, we don't offhand know anything about that, but being inside a solid sphere, what you are is you are just experiencing the total gravity from two sources. One is a planet below your feet, and one is a shell above your head. And the two claim, and that just means you're simultaneously experiencing the two cases that are simple enough for us to know anything about: the shell case and the inner case. The shell case, so this is, I don't know what I mean by a head, I mean above head. All the mass above your head cancels, in other words, from claim number 2. And all the mass below your feet is accounted for by Antonio's substitution. So the net gravitational force that something experiences within a solid sphere, here's the conclusion of this. It's a lot of premises to accept at once, but the conclusion, and this is also the answer to the homework and all of that. So, I mean, this counts as a posting. I'm saying that the net gravitational force, if I'm going to say it as best as I can, even including directions, on something within a solid sphere, with the given parameters we said, ends up looking like this. Okay, a whole new force. It's not a contrast with between any two given points. Gravity acts like this, the below, but from the entirety of a solid sphere acting on a point within, it acts like the top. Those are very different. They're both have the same dependent variable, both have the same independent variable, but the dependence is so different. What this says, what we just got, and I know we're just about done with class, but this is and of course I'll post more solutions and all of that, but this is like the most newest thing in this whole packet anyway. And again, there's already recordings about this if you want to check it. But what we're trying to say is, oh my God, once you go into a sphere, let's just take the limiting case. If you go inside the sphere, inside the Earth, check out where lowercase r is 0. Like if you're at the center of the Earth now, everything's pulling on you from the outside. And just as you might expect, if you're at the center of the Earth, your entire force of gravity is 0. If r is 0, of course F is 0. And that makes sense. In other words, you're weightless at the center of the Earth. And that does make sense, because if you had any weight at all at the center of the Earth, which way would it pull? Like what would it mean to fall down at the center? Which direction? All directions are equal. So it actually does make sense that there's no preference, can be no direction, no preferred magnitude. At the center of the Earth, you're weightless. As you start walking out from the center in your mind, right? As we start inching our way from the center, we experience more and more weight. Like the lowercase g number, the thing that you all know is 9.8, is not 9.8 at the center of the Earth, it's 0. As we start climbing out, according to this function that we just derived for the first time, as we start climbing out, the force of gravity on us gets stronger and stronger. Like not weak, right? If you get farther and farther away from the sun, the gravity from the sun gets weaker and weaker according to this bottom expression. Weaker and weaker, inverse proportional to r squared. Here, r is in the numerator. This is very different. If you start walking out from the center, your weight gets more and more and more in this linear way. So if you are halfway out, and I'm not saying this just yet is realistic, but we're just building towards reality. If you imagine yourself at a point halfway between the center of the Earth and the surface of the Earth, you will weigh exactly half of what you normally do. Like this is saying your weight is directly proportional to your distance from the center, and it keeps building directly proportional that way. And then, oh, I'm watching the clock. I won't do what I did yesterday. But if I'm just looking at if I'm really doing this properly, this is lowercase r, and this is capital R, and this is FGR. Like you start walking out from the center, your magnitude gets bigger and bigger, but in a negative way. It's like negative because it's pulling you towards the center until you get to the surface of the Earth, and then your gravity goes like that. Like this is an upside down straight line and then upside down hyperbolic thing, right? Your weight gets lower and lower as you get farther away from the center of the Earth, as long as you're outside the surface. Before you get to the surface, your weight is going up and up magnitude-wise linearly. Okay, I'm saying a lot. You have to think about that. That's the conclusion of what we just got. Who cares? What does that have to do at all with any of our material that we've been studying or the exam, like, why is it fair for me all of a sudden to bring this up? Well, first of all, we do need to bring gravity back into our lives for the future, but really why all this is fair is, and this is where I'm going to stop, but look, if you follow this at all, we just decided the force of gravity under nice special conditions of being inside a solid sphere, we just decided that the force of gravity does something like this. And that capital R is a constant, right? So even though something is being cubed in the denominator, don't be intimidated by that. It's just a constant being, but we're saying that the force looks like this. And just about done, yeah, just about done, like two, sorry, hold on a second. Yes, yes. Sure, I think, sure. All right, okay. Sorry. Okay, we have this. R is position or displacement variable, right? It's like X or something. Hopefully many of you see where this is going. All of a sudden, the next in the question, I'm asking you things about time, like how long would it take a rock to go from one edge of the tunnel to the other, blah, blah, blah. To cut to the chase, hopefully many of you recognize, if you view R as a position variable, or if you understand that what we're really saying here is, and you understand that, and I'm saying this fast, but this is how this becomes an exam, I guess. This just means constant. If you understand that we got constant, then what you realize is that once you're inside the solid Earth, the force of gravity is directly proportional to displacement from center of Earth, i.e. the acceleration is directly proportional. The rate of change of position with respect to time is directly proportional to position itself times a negative sign. Like, to cut to the chase, and I know there are some of you who totally got this, and I wish I could hear you say it for your satisfaction, but just because of the clock, I'm saying it. Like, this is our differential equation, right? This is saying that inside Earth, not outside, inside Earth, you make a tunnel from one end to the other, what you get is a simple harmonic oscillator. You get gravity itself will provide a invisible spring that will bring things back and forth through the tunnel in the same way that they would ever go across any kind of spring. In other words, we're literally saying, you know, and I'm going to, this is a harmonic oscillator that can be solved just like homework 3, the heat harmonic. And that's the point of all this. And I will post a solution to this specifically, believe me, but you know, if this is true, like if we just decided that this was true, even if we didn't know what R stood for, if it stands for any kind of variable and all the rest are constants, then this is a harmonic oscillator, which necessarily means this, right? And omega is necessarily the square root of whatever's inside those parentheses, right? And this is where I'm really going to end, right? So omega necessarily is this. And those are numbers once you specify planet, you know, the mass of the planet. Oh, and sorry, no, it's not that. The masses cancel out. The masses cancel out and F net equals ma. So omega is that, and T, like, so the frequency is this. And the period therefore is this, and that's what you need to. So you could plug in numbers, and you'll get 42 minutes. If you actually, it takes 42 minutes to get to the other side. I'll pick up on that on Monday, but if you want to check, and if you've ever read any Douglas Adams, perhaps there's a connection. But the answer to how long it takes to, in other words, the period is 84 minutes. It takes 42 minutes to get to the other side. I'm talking way too fast, but that's a lot. But what I'm trying, the whole point of this exam is simple harmonic oscillation is everywhere. So either it sneaks up on you through data that you build and recognize cosine graphs, or it comes in at you through the differential equation. You want to be able to go back and forth between the differential equation and its solutions for harmonic oscillators. That's what's just sweeping through the whole exam, plus those vectors, which I will post solutions and talk more about Monday. Remember, you take this exam after we're done with class Monday. So you can still ask questions and stuff Monday. It'll be sort of up to me how to manage that, but things will be, you know, everything will be posted by then, but you can still ask questions Monday. Also, I'll inform Wu, well, you can also use lab time, however Wu lets you. Please go, if you're late for lab, please go. I'm done. I'm gonna hang just for a second if there's any emergencies, but Sorry to keep you so long. I hope this was helpful. Please go.
Excuse me?
Yes.
Can I ask you some questions, please?
I think so. Yes. I mean, yes, you can. Wait, where are you, Jessica? Wait, who?
Yeah, that's me.
Okay. Yes, please. Yes.
So I'm just kind of confused about where
About.
Sorry, that's not me. There's someone else in this room. I'm just confused about where omega came from in the equation towards the end.
Oh, that's a very clear question. That's a good question. But just now, like where omega came into play in this gravity thing that I'm talking about right now. Is it?
Yeah.
Oh yeah, no, that's a great question. That's sort of the leap of the whole thing, right? It's because, all right, I'll slow down and back up. Like, right, and you're totally right. This is the point of it. Like we think we're talking about gravity, and then all of a sudden it's back to this, our normal material of omega and oscillators. And there is a connection there, but that's the important one to see. So let me think it's after. Yes, this is after class. You should go, like, I'm just answering questions now. I'm sort of sneaking in whatever office hours time I could do right now. And again, I'll make myself available like Friday morning or so. I'll send you all a post, but you should go right now. You are not, you can stay and ask questions, whoever you are, but I'm not trying to hold anybody. You should go to whatever you need to do right now. This is not class. This is after class, whatever that means. But all right, this is a good question. She's saying, where did the omega suddenly creep into this whole gravity discussion? Okay, we did all the hard gravity stuff for like an hour in order to get to this point. Like we found something that looks like this. I'm leaving, now there's like I'm leaving the vector stuff, I'm leaving out of this for the moment. I'm not, because I'm just worried about the vector, but I'm just worried about magnitudes. But we got something that looked like this, okay? And I'm not saying, like, we did all this gravity stuff and we got to a point where all of a sudden, whereas we started with an equation that looked more like this, like had a lowercase r squared in the denominator, we ended up with an equation where lowercase r is no longer squared. It's now in the numerator. And there's this capital R cubed thing all of a sudden that there wasn't before. That's just a constant. But I'm saying we now have an equation where lowercase r, the variable, is in a different place than we've ever seen it before for gravity. Oh, so this is dependent variable. Oh, well, actually, wait, let me not do that yet. Are you with me? So that was like a gravity point. But then I'm saying that R stands for position or displacement from
I thought R is like the distance between M1 and M2, little r.
Yeah. No, very good. Well, wait, it's the distance. That's very good. For always, R is the distance between the centers of any two M1 and M2, right? So you're totally right. R means the distance between two particles, two masses. If they are literally points, then it just exactly means that, the distance between the 2 points. Once we're talking about something being big, like here, like M1 is this big solid sphere, and M2 is just this little particle, then we mean the distance between M2 and the center of that big sphere, M1. In other words, whenever one of the masses is big, then we're measuring from its center. So R here means the distance from the center of M1, like the center of that whole big planet or whatever, all the way from there to the little particle M2, which is located somewhere within the planet. Is that cool so far? So R is you're right. In other words, R is the distance between two things, but it's the distance between a thing and the center of a big thing. The center of, okay.
So maybe I didn't understand like the very beginning, and that's why, because I kind of also lost you when you were talking about how a particle outside of a sphere will be pulled by a force inside the sphere. Like, I don't get that.
Oh, wait, right. So you do get, though, it sounds like what you do get is, in general, whenever we say about pull or gravity, or like whenever we're saying a force from something to something else, the first thing we're supposed to think about is like one dot pulling on some other dot somewhere. Like, and I think you do get that, right? Like M1 could be some piece of dust somewhere in the world, and M2 is some other piece, some like electron or something, and they both pull on each other through this force of gravity, is what the law is supposed to be saying. But then, and I think you get that. I don't think that troubles you. Then we're on making things complicated now, like where we're getting one step more complicated. We're saying, okay, that's all the law tells us directly. It tells us how any one little bit of stuff pulls on some other bit. But what do you do if you want to be realistic and you actually, like, nobody cares about just some one little electron. People want to know how much does the whole Earth or the whole sun or some big like star or planet, some big round body of mass, like we want to apply gravity to that. And what I'm saying is that we have to be careful in a way, like some big body like Earth is a huge collection of tons and tons and tons of little electrons and stuff, each of which is exerting gravity. Like, it's not really that the Earth exerts gravity, it's that all the little bits of Earth exert gravity, and all those bits are everywhere in Earth. Like, each one of them is put, so if I'm standing on the surface of the Earth right now, like in New York or whatever, then all the bits all over the Earth are pulling on me. The parts of Earth that are toward the center of Earth are pulling me down toward it, but also like England, is pulling on me, and like everything in the world is pulling on me. Everything from the world, like trees in Australia, are pulling on me in all the directions of the sphere. So offhand, it's not obvious, like, how do they all add up? Like, they're all pulling on me. Like, what direction do I end up going in, or what? Well, it does turn out that as long as I'm standing outside this round ball, like as long as I'm on the surface of it, as I am now, or even if I go up to a high building, or if I blast off a little bit far away, like in outer space, like, or in an airplane or something, as long as I'm outside the surface of the sphere, it turns out that all the dots add up together nicely to actually pull on me, as though they all pull me toward the center. Like, they all add up as though there was just one dot at the center pulling me toward it. Like, and that's how everybody treats the Earth. They're like, oh, I'm falling down toward the center of the Earth because, the center of the Earth pulls. What I'm saying here is actually everything in the Earth pulls, but it all adds up to act as though it's all coming from the center for reasons that we have to discuss more. But I'm saying right now it's true. But wait, are you with me so far or no? Does that make sense? So
I think you told me that like particles pull on each other in the world.
yeah, I am saying that, yes.
Okay, then I understand. Yeah.
Oh, okay. So then in the end, how this all that gets back to the material for the exam and stuff is, it turns out if we're careful, like, and it's a lot. All of a sudden, I'm saying all this stuff about gravity. I'm technically reminding you, but because of all this stuff about gravity, it turns out that a certain gravity situation, like, that is, you imagine yourself going underground, like deep underground, below the surface, imagine that the Earth is this big solid ball, and we're somewhere underground between the center and the surface. If that's where we are somewhere, it turns out that the force of gravity acts like this equation that we derived. Like, it turns out that R is in the numerator of the equation. That is, the farther out from the center you are, let me start again. If you're right at the dead center of Earth, according to this equation, if R equals 0, it's like you're standing at R equals 0, so you're nowhere away from the center, then you plug in 0 to the right side, you'll get 0 on the left side, meaning you have 0 weight. This is true. At the center of the Earth, you don't weigh anything. You're not being pulled anywhere, because where would you be pulled? You're already there. You're at the center. If you start going a little farther out, this is saying the farther out you get from the center of the Earth, the more weight you have. That's not where as long as you're still within the solid sphere, if you're and I'm not saying you would really do this, of course, I'm just talking about the math of it, but if you started crawling out from the center, making a tunneling your way out toward the surface of the Earth, the closer you got to the surface, the more your weight would get heavier and heavier, and the more that G number would be getting closer and closer to 9.8. So like, if you're halfway to the surface, you would weigh half of what you normally do, and that 9.8 number that we always use in lab and stuff would be 4.9 instead of 9. That's what this equation is saying. And I'm saying, oh shit, excuse my language. I'm saying, oh, wait, that sounds like a spring. The farther out I am, the harder I'm being pulled. And there's a negative sign, like i.e. the farther out I am from the center of the earth, the more I'm being pulled toward the center of the earth. So if I'm really far away, I'm being pulled really hard toward the center. If I'm twice as far away, I'm being pulled twice as much. And if I'm dead at the center, it's like an equilibrium spot where I wouldn't be pulled at all. Oh, that sounds a lot like a spring. And mathematically, I'm saying, oh, it is literally, oh my God, even though there's no metal or coils there, whoops, sorry, it is a spring because it's F net equals MA. Like if I do F net equals MA here, yeah. So I put in MA for F, and I remember that A is the second derivative of R. Like R here stands for position. R here is like X, you could say. I mean, I don't know if that helps. I'm saying R here is measuring the same thing that X did for us in a few other problems. And it looks like the acceleration is directly proportional to the position. Man, I'm looking at the chat while I'm talking, which I really shouldn't do. And so suddenly I realized, oh my God, this thing is an oscillator. This has that same math, that same differential equation that we're sort of trying to teach ourselves to recognize from a mile away and to be able to use. I'm saying in the end, in other words, instead of X, we have R here. And instead of K over M, we have GM over R squared. I'm going to try to write this. We had this, but now we have this.
And can you still say that it equals MA?
Oh yes, because this is it's the only force acting on you. Yes, good question. As long as you drop something into that tunnel or whatever, and nothing else is acting on it besides gravity, yes.
So when you're in the circle, you said that your weight increases as you crawl out. Is that only G that changes, or can your M change as well?
Oh, that's a fantastic question. That's a great, and surprisingly, even though that goes really deep, I can answer that surprisingly concisely. It's a fantastic question, and also shows you know something. If your weight is mg, that's totally right. Like if you think of weight as lowercase m times lowercase g, I'm saying that as you crawl out from the center, what's totally changing is your g.
Thank you, Professor. Thank you. I have to leave to the meeting. Okay. Thank you.
No, thank you for your note too. Thank you for your chat.
Thank you. Bye bye.
Thank you. I'm totally saying that it's your G that increases and your M holds steady. And that's a really important point. Like your mass, your number of kilograms, wouldn't be affected at all from the center to the edge. Like you'd be just as hard to throw. If someone's trying to throw you across the room, you're just as hard to throw as ever. But the G is going to go up and up. So when you're halfway there, the G is at 4.9. And when you're all the way there, the G is at 9.8. That's what changes, meaning it's hard. There's more and more pull on all of your kilograms toward. Well, and your question is great. It's the M that doesn't change, and it's the lowercase g that would change. And together, that means there's a change in your weight. That's right. Is that, I mean, I think, does that answer you?
Yeah, I think it does answer my question. Also, is R hat equivalent to like the I hat, J hat, K hat that we
Right,
spoke?
it's that whole concept. Yes, I'm taking the hat from that whole business. Right, I wouldn't assume you know about hats otherwise. Yes, but so I'm saying just like, so hat means the unit vector for a particular vector. So wait, let me see if I can write this quickly. Like, right, if we had some random vector A, and it was just some random vector that pointed in some direction and had a certain length, then yeah, then we were saying the hat meant necessarily the vector A divided by its own length. Yes, I'm saying R hat means the pure direction of R, but none of its length. It means a vector that points from M1 to M2, but by definition only has a length of 1. So yes, I'm using that. It's just like I hat, only I hat by definition it applies to the x-axis. R refers to one object pointing to another, and I refers to an axis of space pointing from the origin. But that's a good question. Okay, cool. Good. Okay, so I think, is that good? For the moment, I will post more things, but I think those are good questions. And Cynthia, is Cynthia here? Cynthia here? Sorry.
Yeah, I'm here.
Oh yeah, okay. Did you have a question? Or are you just hanging to see what's what, or do you do?
Oh, I'm just hanging out right now to
Okay,
see
cool.
what was
Okay.
happening, but yeah.
Okay, that makes sense. No, that's totally. I would do the same thing. Well, I did the same thing. That's why I gave him this far. And so Jessica, you're good. Yeah.
I have more questions. I don't know if anyone else does or if you have to leave. I mean, I
Well,
could
I
say.
think. All right. No, I think you're the only ones. Oh wait, maybe there are. I should. No, I could take a couple more. I should leave like within 5. Let me see what I can do within the next 5 minutes. Or Grace or anybody who is here and waiting to ask a different question. Maybe if someone else wants to ask a question first, if it's not private, just. But if you're just here to have, if not going once. All right, to ask one more. Okay. Oh,
They're like really long, so I guess that I could just wait till your office hours and ask.
Okay, if you think, no, I appreciate that you're being careful about or that you're thinking about it both ways. Definitely I appreciate that. Keep track of them for sure. Like definitely do please write them down or whatever the questions that you have. I will try to have the office hours Friday morning, but then also please remember, Monday, we still have class and, I will answer good questions on Monday. What I don't want to do is go in Monday where I'm sort of reserving the right to just move forward if I want is if I go in Monday and like no one studied at all and no one knows anything and then everybody's just like, can you teach us the material for the first time? Then that's, I think, a waste, so I won't honor that. But if someone like you has already thought of these things and has been holding on to a question, certainly Monday would not be too late and would be very welcome to ask. And I'm not saying that, so keep track of them, but I'll try to do the office hour thing Friday also, because these are good questions so far. But always, please remember also, I only understand this stuff because I tried it so many. I mean, try the stuff at home too, and bang your head against the wall too, because it's only gonna make sense to you your way ultimately. But these are great questions so far. Anybody? No, you're good. You're good.
I just feel like the homework was hard because like I don't feel like I have the power to like make all these assumptions like what you did. Like
Oh yeah. Oh no, that's very fair. I could say a quick thing about that. This is what the harder the homework feels right now, especially these last couple like out of nowhere, especially because of all these assumptions. That's all true. It is. Like I find this very hard. It's only not hard for me because I already know what's about to happen and I've done it before, right? But it is hard. But on the test, what you're going to get on the exam, what you're going to get is things like this with these same assumptions. Like I am not trying to teach you how to, when you go into the test, it's not going to be a whole new set of wild, crazy new assumptions, nor am I going to ask you to come up with new assumptions. Like these are weird enough assumptions that we're practicing with them now. So yes, I couldn't expect you to come up with all this on your own. That's why I could expect you to try and get it. And then by the time you come to the test, it won't be the first time. That's the best way I could put it right now. But yeah, these are not just examples. Like if you study this, sometimes good students get worried. Like if I just keep looking at the same example over and over, it's only one example, I won't be ready. No, that's wrong. Like anything we've done in class, the best thing you can do is cover it up and see if you can reproduce it on your own. Literally, like if you want to pretend you're memorizing, just see if you can produce these exact same derivations on your own without looking. That totally does not waste your time. These are not just a random example that then the test will be different. These are the thing. So if you can reproduce it on your own that many times, then you really are not wasting your own time. You're just, even if a couple times you don't think you get what you're doing, but you're just like reciting it. You see what I'm saying? Like there are a lot of out of left field assumptions. That's not going to be out of left field on the exam. If you've just try to cover it and do it over and over. Don't worry that it's the same thing, if that makes sense. But I'm saying that to everybody. I think physics is very hard. But it's hard in a surprising way. It can be made much easier if you trust me and treat yourself like a kindergartner, not like a college student, like for real. And that's what I do. Anyway, people who.
Yeah, I think I've learned a lot, even though like it's only been 4 classes, and yeah, I think I really like I understand your method of teaching. Like it just really sits well with me.
Oh, well, that's very nice of you to say. I hope that continues. And look, you've been totally engaged. Obviously, I'm sure you feel in your mind confused or behind or something. Like it's, it sounds like but you're clearly here and present and asking all these things the whole time. And I know who you are. And I'm saying this also again to anybody who's listening right now. Like you're in the correct space. Someone who wasn't worried at all and was just like, yes, this is all obvious. Yes, it's all obvious. Then they're going to be headed for a fall because it's not that obvious until you do it yourself. But everything you've been doing, like you're cruising to do well on this. You are like, you are cruising to do well, even if you don't feel perfectly on the exam. I guess I'm saying your style of learning works for me too. So that's all. Yeah, so I think we're good. But no problem. All right, so I will go before I get myself embarrassed, and onward and upward, everybody. Okay, I'm leaving
Thank
because
you so much. I
thank
really
you guys.
appreciate it.
Not
Bye.
at all. No, this is fun. Thank you guys. Okay, bye.